I want to use the last concept that we've seen during the SSH lessons, which is the jump host, as a segue to the next concept, which is virtual private networks. And a virtual private network is basically a secure encrypted connection over a public network. So a private network is the one that you have at home. A virtual private network tries to emulate the security of a private network that you have at home, wherein you own all the devices that are inside your house, but leveraging the public network. So suppose that you have remote workers that want to log in into the corporate servers. We don't want to expose all the traffic that goes from the house of the remote worker to the corporate office that contains sensitive data about the company. We don't want that to be intercepted by anybody. So a clear aspect of a VPN is data encryption and security, as to allow remote access to private networks, as to protect the privacy, and has to bypass geographical restrictions. So think about global remote workers. They can work from wherever they want, and they need to be able to access the corporate facilities. So the VPN architecture is extremely similar to what we saw in the Bastion host, in the jump host lecture for SSH. We have a client that establishes an encrypted tunnel with a VPN server. All the routing is done through the public internet. So client can be in India, the server can be in the US. Everything goes through the public internet, encrypted, so the public internet doesn't know what's in there. And the VPN server takes those packets, decrypts them, and sends them to the private network. And now the private network, what they see is as if the VPN server generated those packets, because we're going to see that the VPN server will need to be masquerading the traffic that comes from the clients. So traffic that comes from the VPN. And this is going to be the same kind of masquerading that we do with the top interface for Qatar. Pretty much the same thing. There are mainly two types of VPNs. You have a remote access VPN where individual users connect to like a corporate network, and this is a client to site connection. And you can think about home workers, home office, and this is the one that we're going to focus our attention on. And then we have a site-to-site VPN. This is a much bigger topic to talk about, and this basically connects entire networks. Suppose you have two branch offices that are one in Germany and one in the US. You want to connect the two offices. This has different kind of reliability requirements, different kind of authentication and security requirements. It's a much bigger topic. What we want to talk about is remote access, because this is one of the most common things that you have to set up as a system administrator. Common VPN protocols and infrastructure that is out there, it's OpenVPN, IPSec, and Wireguard, and those are the three ones that we're going to use. And then there was a time when there was the point-to-point tunneling protocol. This is very old, nobody uses it anymore. We're going to see OpenVPN, IPSec, and Wireguard. OpenVPN and Wireguard are layer 4 VPNs, so they run on top of either TCP or UDP. And IPSec is a layer 3 protocol, so works at the IP level, doesn't run on TCP or UDP, in fact has its own small header to perform the encryption and handshaking and all the stuff that it needs to do. So how does this compare to SSH port forwarding that we already saw? Well, SSH port forwarding, it's meant to be used just for one application, meaning that you map a port into another port, and that port is associated with an application. For example, here we forward the local port 8080 to web server 80 via a jump host. So we are forwarding a port to another one, and This is what's called application-specific tunneling. What we want to do with VPNs is basically tunnel all applications inside a single secure channel. So these are the key differences between VPN and port forwarding. VPN sends all traffic, while SSH port forwarding is application level. The transparency of a VPN is completely transparent. We're going to see that all the VPNs are going to be NAT friendly. It's going to be as if the traffic is being generated by the VPN gateway from the perspective of the private network, while for SSH port forwarding, we've seen with the remote port forwarding scenario, we had to do a double tunnel, first a remote, then a local, for making it work. VPNs are much more complex to set up respect to SSH port forwarding. Probably the port forwarding lecture were 10 minutes. VPNs, they don't run less than 30 minutes, so it's quite more complex. In terms of performance, VPNs are extremely optimized, while SSH is not really meant for performance. VPN support all IP protocols. SSH supports only applications that run on TCP and UDP. And the authentication is, for VPNs, we're going to see that we have to set up a specific thing called certification authority for both OpenVPN and IPSec, while the Wireguard VPN looks a lot like SSH key-based authentication. And here's a brief summary of when to use each solution. It's not really like black and white. You really need to talk with the corporate and see what they need. Tunneling is this concept where we take the original IPv4 packet and we add a tunnel header. And the tunnel header can be a layer 4 header, so a UDP header, which includes also the IP part. So it's a IP plus UDP header, like for OpenVPN and Wireguard, or it can be a simple IP header like IPSec. So the idea is to wrap the original IPv4 packet inside a larger IPv4 plus layer 4 for certain VPNs. And the key concept is to encrypt the original IPv4 packet, so that what we can do is the new tunnel header looks like a normal IPv4 header that can be routed through the network. Once it reaches the VPN gateway, the VPN gateway removes this tunnel header, decrypts the payload, which contains the original IPv4 packet that then sends to the private network that is behind the private gateway. So we have the tunnel endpoints, which are the client and the VPN server. And this is completely transparent to application. We have a couple things that these are common tunneling protocols. There's OpenVPN tunneling, which is extremely similar to what Wireguard does. This is an older one, generic routing encapsulation, but there's IPSec tunnel mode, and we're going to talk at length of IPSec tunnel mode in the IPSec lecture. There are a few advantages for using tunneling. There's network transparency, meaning that tunneled packet survive also network address translation, because they're just as any IPv4 packet. So it's protocol independent, flexible routing option, and we can encrypt the original packet as if it was a payload. But there are challenges, because you have increased packet overhead, you're adding a header, and this has potential MTU issues. We've seen in the introductory lesson to all the protocols that one aspect of the Ethernet protocol is the maximum transfer unit, which is usually 1500 bytes. And when we add an header for tunneling, we reduce the amount of payload that we can send, the amount of meaningful data that we can send. And at that point, if the original packets were created with the full MTU in mind, and then we add an header, we run the risk to start fragmenting those packets. because they're bigger than the MTU, and this creates all sorts of performance issues. And so it had complex troubleshooting and a huge performance impact if we're not aware. There are dynamic protocols, which are called like path MTU discovery, that allows to dynamically find out what's the MTU, for example, over a VPN, and the application can say, hey, this particular path on the network doesn't accept an MTU more than 1400 instead of 1500 before we start seeing fragmentation on the network. So this is the use case. The purpose of a VPN is to enable secure access to corporate resources from remote location, being a home office, a user that is logging in from Starbucks or another branch of the same company. Route everything on the public internet, because the company cannot physically lay a wire across the ocean or lay a wire to the Starbucks where the employees working from. And so we need to use the public internet, encrypt everything, ship it to the gateway that then sends to the server and the resources inside the corporate network. There are key components for a VPN. There is a VPN gateway. We will call it a VPN server. Sometimes you call that concentrator. There has to be an authentication system, and we're going to see that for OpenVPN and IPSec, it's going to be a certificate-based authentication, a fancy way of saying public key. But there's need to be a certification authority that issues those certificates. And then there has to be a policy engine. And we're not going to talk about this in this series of lectures, because the policy engine really depends on the policies for the corporation. But what the policy engine does is basically tells what kind of users can access what kind of resources, when we have to revoke a certificate or access to a VPN because either a key has been compromised or the certification authority has been compromised, and all sorts of rules in terms of how much bandwidth we can allocate to users and whatnot, because you can think that the VPN gateway acts as a concentrator, and so the more users are using the VPN, they all clash onto the VPN server, and there's not a really meaningful way to load balance VPN connections, at least not cheaply. We're going to see that all the VPNs that we're going to see, OpenVPN, IPSec, Wireguard, are going to use Diffie-Hellman key exchange. We already saw it during the SSH lessons. I put a refresher here just for your own sake. The authentication problem on the VPN is fairly simple. As in SSH, we want to verify that users are who they claim to be. We have a few common authentication methods, username and password, that we're not going to use in this case. Digital certificates, and is the main one that we're going to use. Pre-shared keys. This is something that we can do for site to site, where the keys do not change, and users, in this case branch offices, are added much more slowly than employees. There's also multi-factor authentication. We're not going to talk about it, but some enterprise consideration is that some of these VPN technologies, especially IPSec, can be integrated with existing user directories such as Active Directory and centralized authentication servers like Radius servers. And this allows the company to scale and to support large user bases of employees. We talked about a little bit of a certification authority, and what a certification authority is basically a private key and a public key that are held by somebody at the company that decides who can join the VPN. And typically, the certification authority is the one that issues certificates for the VPN server and all the VPN clients. And the way this typically works in practice is a new employee joins, he gets asked to generate a request for the certification authority. The request can be shared on the public internet. Typically, it's sent with an email to the system administrator that manages the certification authority. The system administrator takes that certificate request, takes the certification authority key, it signs that certificate, and it sends over to the VPN client both the certificate for the client and the certificate for the certification authority. And the certificate for the certification authority is going to be needed to tell the server, hey, I've been issued that certificate by this guy, who is the same guy that issued your certificate. And this is basically how it works. So for both OpenVPN and IPSec, we're going to see that we're going to need a central entity that's going to issue certificates for all the devices that are going to join the network. And there are some benefits, which is strong cryptographic authentication, no passwords to be compromised, it's scalable for large organization, and supports certificate revocation. So suppose at a certain point an employee leaves the company, you want to revoke that certificate and let all the other devices know, especially the server, that that certificate cannot be used anymore to join the VPN. It is quite painful to set up because we have to set up a public key infrastructure, so a PKI. The certificates needs to be distributed, and we have to manage the life cycle of those certificates because certificates expire. No matter how long we make them last, the lifetime of a certificate is limited, and when that lifetime comes due, the certificate needs to be renewed. And so the company either has to have a automatic way of renewing those certificates, or is the manual system administrator job to reply to the email, hey, I can't connect to the VPN. Do you know why? Yeah, your certificate expired. Here's a new one. When a client connects to the VPN gateway, a couple things happens. The most important one is that the server, the gateway, assigns a virtual IP address for that device, pushes network routes for the private network to the client, meaning that now the client, to reach the company server that is behind a VPN gateway, knows that has to go through the VPN gateway. So once the encrypted tunnel is established, all the traffic that goes to the company server now is redirected through the gateway, and the client knows how to reach the private network behind the gateway because the gateway pushes those routes. And it can do a bunch of different things. It can push DNS servers to make sure that we only use the DNS servers within the company and the DNS search domains, supposing that all the hosts in the private network use a fully qualified domain name under the DNS for the company. We can have a search domain pushed through the VPN connection establishment. Another thing that we can configure at setup time for the VPN is how much tunneling we want. We can go two ways. One is full tunnel. Well, once the client connects to the VPN, all traffic goes to the VPN. So if the client is an employee and uses his company laptop to watch Netflix, that Netflix bandwidth goes through the VPN gateway in your corporate office and is gonna consume bandwidth, as you can imagine. That's the downside. The flip side is that now all traffic goes through the VPN, meaning that you are sure that there's no leakage of information. On the other hand, split tunneling redirects through the VPN gateway only the traffic that is related to the company. So for example, access to SSH servers, fax machines, and internal chats and whatnot. While all the traffic that is not related to the company goes through the standard route, which is the internet service provider for the client, without being encrypted and sent through the gateway. And we're gonna see only split tunneling, but knowing that a full tunnel is possible as well. Now that we've seen the key concepts of VPNs, we can start looking at a few implementations of VPNs in Linux, and one is OpenVPN. And we will use OpenVPN for basically tunneling all the traffic from one host to another one. And OpenVPN has a lot of very interesting features that allows us to tunnel over UDP or TCP. We're going to see that we're going to tunnel over UDP because we want to let the application decide if it needs retransmission or not. If we tunnel TCP inside TCP, this can cause all sorts of issues because we are basically nesting two retransmission state machines one into another. So this is why I advise you to always use UDP for VPN and let the application that tunnels packets inside the VPN decide if it needs retransmission or not by sending UDP packets or TCP packets inside the UDP tunnel. A key element of OpenVPN and all VPNs for that matter is the creation of a public key infrastructure. And a key element of a public key infrastructure is a public key certificate. And a public key certificate is data structure that we're going to see in the next slide that binds a public key, as we saw in SSH, to an identity, which can be what is called a common name. It can be a URL. It can be whatever. So an example of certificate is when you go to www.google.com, you see that small lock that shows that you're using HTTPS. And on that HTTPS stream, there's a certificate that certifies the fact that that host that you are reaching, his identity has been verified by a certification authority that issued that certificate. And so the binding between the identity and the public key is granted by a trusted certification authority. And provided that we have the certificate authority public key, which is, again, public, we can verify that the certificate is valid. So the binding between a public key and an identity is valid. So public key infrastructure consists of a certificate format, a relationship among certification authority, mechanism and policies for issuing and revoking certificates. And we're going to talk about the mechanism, while the policies, it really depends on the company you work on. And storage services mainly means how we distribute certificates and keys. And again, this is part of your company policy. Who issues the certificate of SCA? Another certification authority. And the key concept here, there are some top-level certification authority that need to be trusted, and those certificates are installed in your operating system. We're not going to deal with certificates issued by other certification authority, but we're going to see in this lecture that we're going to build our own certification authority that's going to issue self-signed certificates. This is the format of a certificate. If you want, you can go on your web browser, click on the log, hit show certificate, and you're going to see all this information spelled out, for example, for Google, for Facebook, for whatever website you choose. One extremely important aspect we have to talk is how the tunneling happens. We've seen that Katara allows us to create a top interface to connect to the internet. Here we're going to use a TUN interface, TUN, which is a virtual point-to-point network device for IP tunneling, which is exactly what we need for a VPN. So what happens? The application that runs on top of the tunnel sends traffic to the tunnel through a socket. That TUN interface is attached to a listening application. In this case, it's going to be either the OpenVPN client or server that takes that traffic, encrypts it, and does all it has to do and sends it to the real network interface card. So this is what is going to happen. We have a application on the client, which can be like ping command, can be whatever, netcat. Then we have the OpenVPN client that created that TUN virtual interface, the app is going to send traffic to the user space end of that interface, that the OpenVPN client then encrypts it and ships it over into the tunnel until it reaches the network interface card of the OpenVPN server that sends it to the TUN interface, decrypts it, and ships it to the end host. And the important thing is that the OpenVPN server has to be a public server, has to be reachable by the client, but the client doesn't have to be necessarily a public or a private. It can be whatever. And this is how the tunnel works. We are basically attaching the IP and the UDP, as we talked about, header to an encrypted IP and or TCP, UDP, whatever packet that we are encrypting and putting inside here. So this is why it's called a tunnel. And of course, we are relying on IPv4, so this thing survives network address translation. It's from the network standpoint is a standard IP packet. Only the client and the server will know that, in fact, inside this packet, once it's decrypted, there's another IP packet that needs to be either forwarded or processed if it's intended for the server. And the first step in building an OpenVPN is to establish a PKI. And in particular, the first step is to build a certification authority that then is going to assign and issue certificates for all the hosts that are going to participate in the network. And the network is going to be like this. We're going to have a R1 that is connected to the actual internet, because we're going to have to download some packets. We have client 1 VPN that's going to participate in the VPN, and we're going to have our server VPN that's going to be our server and certification authority for the entire network. Our server VPN is going to give access to client 1 VPN to the subnet that is behind it. So client 1 VPN does not know how to reach through R1 the host, but we're going to see that by creating a tunnel between client 1 VPN and our server VPN, we'll be able to reach what's behind here. And this is exactly the scenario that you're going to face in your professional lives. Imagine that this subnet here, the 192.168.0.0, is the private network of the corporate office. The server VPN is either the border router to your private network, or it's a physical server that is going to act as a VPN server. And client 1 VPN is the employee laptop that is connecting to the subnet, the private network of the corporate from the airport, for example. And we want to be able to protect all the traffic and encrypt all the traffic until it reaches a safe harbor, which is the private network of the corporate, which we will assume is not compromised, for example. And the first step is to build the certification authority. Now, we are in Skeleton Lab VPN, OpenVPN, and there are a couple of things that I want you to look at. And the first thing is that we have a create.ton.sh inside the root folder of client 1 VPN and our server VPN. That are the two devices that are going to be joining the VPN. And we can take a look at what's in there. And there are a couple of things that are needed to create a ton pseudo device on the containers, because the kernel that's running on the containers hasn't been compiled with the tun support. So we have to create a made up device for OpenVPN to use for its own operations. Then we have inside the startup scripts of both client 1 VPN and the server VPN, we have a install of OpenVPN. And with OpenVPN, we install also EasyRSA. And the original directory of EasyRSA is this user share EasyRSA, but I want it to be in etc OpenVPN, so you have everything into one place. Now we can fire the lab. Let's give it a minute. We are going to assume that the certification authority is on the server VPN, in this case, so the certification authority and server VPN are going to be the same device. And let's add into OpenVPN EasyRSA, and let's do a EasyRSA. I need public key infrastructure, and we can do an EasyRSA build CA. It asks us to have a key passphrase for the PKI, for the certification authority. Choose whatever you want. And then it asks us to enter a passphrase for the key that it's going to be used to sign all the certificates for the devices that are going to make requests to join the VPN. Here's where you can change the common name of the certification authority. The default one, it's fine. And here we just created our certification authority, which consists of two things, basically. The ca.crt, and if we go in private, we have the private key that's going to be used to sign all the certificates that are needed for the server and the client. The second step is to issue a certificate for the server. Now, what we can do is create a request for the server. Now let's call it R. Let's call the request same as our host name. Let's create a passphrase as well. Common name is fine. And this is where we have created the private key for the server and the request to be signed by the certification authority for our server VPN. Now, what we can do to complete the key and certificate stuff that we need for our server VPN, we can sign the request. And here we have to specify if this is a client or a server. I'm going to say server and name. Here it asks us to confirm some details. This certificate is going to be valid for 825 days. We have our server VPN as common name to confirm. Let's type yes. So it asks us to enter the passphrase that we entered when generating the certification authority, especially the PEM password if you inserted two different passwords. And you can see that now we have a certificate for the VPN that has been signed by the certification authority. So this means that our server VPN is allowed to join the network that belongs to this certification authority. Now we have everything in terms of keys and certificates to run the server, we need one last thing. And if you remember from the SSH lessons, we talked about diffie element parameters, and those have to be like common and shared. So we can generate those diffie element parameters here, and it's going to take a while because it's finding a large prime number. And here we have. So let's copy everything that we need inside the root directory, the home folder of the root user. So we need the diffie elements. Then we need the certification authority certificate to authenticate all the clients that are going to join the network to make sure that the certificate for that client has been issued by the same certification authority. Then we need the issued certificate for our server VPN. And then we need the private key for our server VPN. So your own folder should look like this at this point. We have cacrt, th.pam, our server VPN crt, and our server VPN. And the last step is to set up a PKI on client 1, generate a request, having signed by the certification authority, and get the certificate back. Okay. Now we gotta do the same things for client 1 VPN, except we don't have to set up a certification authority here. We just have to generate a request, send it over to the certification authority, have it signed, get the certificate, bring it back. The private key does not have to leave client 1 VPN, because otherwise it means that it's been compromised, and then we have to revoke it. And our server VPN and OpenVPN, especially EasyRSA, has mechanism for revoking keys. Now let's go to etc, OpenVPN, EasyRSA, I need PKI, has been generated. Now what we can do is EasyRSA generate a request for us. Here it asks us to have a new. Perfect. Now we gotta move the request here over to the certification authority. What we can do is we can move it to shared. And now that it's in shared, we can go to our certification authority here. Import the request. For client 1 VPN. So the request has been successfully imported, and now we can sign it. As a client for client 1 VPN. Let's type yes. Again, the password for the certification authority. This is where we sign the certificate for the client that's joining the network. If you lose the private key and the password associated to it, the guy that stole the key and the password can forge certificates and everybody can join the network. So you don't have a private network anymore. So you should guard the key and the password of the certification authority as the most important thing that you have. Okay, so we got the certificate. We can move the certificate back to the shared folder. And now we can move the shared to our own directory. And we can now copy all the other common stuff that we needed on to the other side, which is ca.crt and dh.pem. Now we can go here and copy everything that we need, and we're missing the client 1 VPN key that we can get from IPSe, OpenVPN, EasyRSA, PKI, private client 1 VPN key here. Alright, so we have everything from a key and certificates standpoint to make the public key infrastructure work on both server VPN and client 1 VPN. Now what we need is to configure the network side of things. Let's start editing the server configuration. So the first thing we want to select is the port where we want to run the VPN server. The default one is the 1194. Then the protocol that we want to use, and we explained in the theory part, we want to use UDP because we don't want to nest two TCP state machines, one into another, one for the VPN and the other for the application that runs inside the VPN. So let the application decide if it needs retransmission or not. The tune. Then we have to select the cipher that we want to use. And let's choose this one, which is AS256 Galois counter mode. It's one of the strongest. Specify the certificate for the certification authority that's going to be used to verify all the clients that want to join the server. Then the certificate for the current device, which is in our server vpn.crt. Then the key. And then the diffie element parameters, which are here. And then what subnet we want to use for the VPN that's going to be generated by the server. And we can put whatever we want, 192.168.100.0/24. So we can have at most 254 hosts on this network. And then remember, we want to be able to reach the subnet that is behind the server VPN. So this is exactly the scenario that you're typically going to find in enterprise networks when you want to have for example, the remote workers to access the server VPN, and the server VPN exposes all the nice private network that is behind it, because there are compute servers, there are all the stuff that the employee needs. So we can push a route through the VPN 192.168.0.0, so /24. It's a client to client in this case, and then the router will do the rest. Topology subnet, and this means that the IP addresses are going to be assigned dynamically by the server to the various clients that want to join the network. And then a little bit of boilerplate in terms of if there's no traffic going on in the VPN, we still want to keep alive the connection. Don't expire the key, do not expire the interface, and we can have a certain level of log to see what's going on. Okay, so we can fire the mux and we can start the server, OpenVPN server.conf. Oh, there's an error. Let's start it. So private key password for the server. And here we have with initialization server completed. Now let's start doing the client configuration. Client.conf. And it's going to be similar words. We're not going to have to specify a lot of stuff. So first thing, we're going to say, hey, this is a client. We're going to use a tune device. Proto is UDP. The server is at 8.0.0.2.1194. If we have a problem with DNS resolution, try infinitely, because maybe one down. Do not bind the interface. Again, persist key, persist ton, root ca.crt. Certificate is root client1 vpn.crt. The key is root client1 vpn.key. Then we have the diff element parameters which are in root eh.temp, and the certificate that we're gonna request is for the server, then same level of verbosity. Let's fire up a tmux session, OpenVPN client.conf. Private key password for the client. And we're in. Let's see what happened on the server. What happened on the server is we assigned a new IP address to this client. And here we have 192.168.100.2 as being assigned to client1 VPN. Here we can see that we assigned that IP address to depton, and we can see that that push route pushed 192.168.0.0/24 via the default router of that subnet. And if we look at routes, now we have the route for the VPN and then the route to the private network. So let's see here if we can ping. For example, we have ton 0. Let's ping the router on the VPN, and it works. Let's ping the router through the VPN on the physical interface on the private subnet. 192.168.0.2, and it works because this is the route that has been pushed with the push route command that is inside the server. And then let's try and reach the P host that is at the other end of the network. And again, this works. So what's going on here is that all traffic is encrypted up until our server VPN through the VPN. Our server VPN then decrypts the packet and forwards it to P host. P host has a default gateway to our server VPN. Our server VPN recognizes that the destination IP address is for the VPN, so it sends it on the VPN until client 1 reaches it. So this is the gist of OpenVPN on a scenario that is pretty much what you're going to face in your professional career, which is going to be setting up one server, which is going to act as a bastion for the private network in your company. And then all the clients are all the employees that either work from home or have their personal laptops, their work laptops, that are going to access the private network through the public internet, for example, at an airport or at a Starbucks or whatever. You want to guarantee the safety of the intellectual property of the company you're working for. Now that we've seen OpenVPN, we can take a look at IPSec, which is the other big player when it comes to setting up VPNs. And the advantages of IPSec is that it's a much more standardized and robust protocol than OpenVPN. It has stronger security, native support, it is transparent, it has some hardware acceleration support, especially from Intel network interface cards. And the other thing that is extremely interesting from a corporate perspective is that IPSec integrates with the existing authentication infrastructure that the company may be running. So supposing that the company is running everything on Windows, all the cloud infrastructure is on Windows, chances are that the company is using Active Directory to authenticate its users, the employees and whatnot. IPSec can be integrated with Active Directory, or suppose that the company is a little bit older and uses Radius as authentication system. IPSec has native support for Radius servers for authentication, but this is nothing that we're going to see. It's just for you to think about. So the core concepts of IPSec, which stands for Internet Protocol Security, so it operates at the same level of OpenVPN, as OpenVPN is transparent to applications, provides end-to-end security. It uses two main protocols, ESP for encapsulating the security payload and provides encryption and authentication, and then has the authentication header, which only uses authentication and it's really not really used. And it's used in two modes. In transport mode, where it protects just the payload, and that's not something where we're going to see. We're going to use IPSec in tunnel mode that protects the entire IP packet, and this is what we use for VPNs, and especially VPNs that operate in remote access mode. So why tunnel mode? The idea is to have the original packet that contains the user IP header and the application data, encrypt everything, tunnel it into a packet that contains the new IP header that targets the VPN gateway, the VPN server, a small IPsec header, and then the original encrypted data. IPsec introduces a security association concept, which is an agreement between two parties on how to secure the communication. And this is typically done at the beginning. An HSA packet contains the encryption algorithm, the authentication method, encryption keys, and lifetime. So this is basically the same thing that we saw in SSH, where client and server are trying to negotiate what language they're going to talk in terms of encryption, authentication, HMACs, and whatnot. The key point is each host on the VPN, the client and the server, will send an SA, and then they will be negotiated when they're establishing the connections, and the keys are periodically renewed for security. I think they do it by default configuration on Linux is every couple of minutes. So even if an attacker captures encrypted traffic, they cannot decrypt it without the session keys, which are generated pretty much like Diffie-Hellman in SSH. And on top of that, even if they are able in those couple minutes to find the key, that key will get changed regularly, so it's pretty much useless. The Internet Key Exchange protocol is the protocol that they use to agree on a set of shared secrets. It provides mutual authentication. It creates unique session keys. It has perfect forward secrecy. This basically extends what we've seen with Diffie-Hellman. You can think of it as basically the Diffie-Hellman key exchange algorithm ++ that supports also various authentication methods. It supports automatic key renewal. There's no manual key distribution needed, and that is given by the fact that we're using Diffie-Hellman underneath. The connection process goes like this, and if it looks a lot like the SSH session establishment, it's because it's pretty much the same thing. So the VPN client initiates the connection and sends the supported cryptographic primitives that it can run. The gateway does the same and sends the key material to generate the keys, which can be the large prime number and the G, the root for the Galois field that we saw in SSH. Then the user provides the identity and authentication to the gateway. The gateway replies with authenticating the client if the client successfully authenticates, and pushes the network configuration for the client. Basically assigns the IP address, populates the DNS if it needs to, and pushes routes as we've seen in OpenVPN. And at that point, both the client and the gateway can start exchanging information over a secure channel. We're gonna try and do the same thing that we've done for the VPN lab, but using IPSec. Now let's head over the lab directories and let's go inside skeleton lab VPN IPSec. And there's really nothing here except for interface configuration and the install of everything that we need to run IPSec. In Linux, the suite that we use to run IPSec is called Strong-Swan, and we're going to use this term called Road Warrior. And Road Warrior is basically the remote employee that wants to connect to the corporate network. So this is whenever you see an RW inside the configuration files that we're using, know that it means Road Warrior. So let's go ahead and let's fire the lab. And let's bring into focus the server and the client. So in the same way that we did for OpenVPN, here we have to set up a certification authority that is going to issue certificates to the server and the client. In the same way that we did for OpenVPN, the certification authority will live on our server VPN. So let's initialize the certification authority PKI, exactly like we did for OpenVPN. So here we are generating the private key for the certification authority that's going to be used to sign all the certificates. And we're going to use this elliptic curve parameter, which is a very, very strong one. You can just forget about these things. It just saying, I don't have all these plugins loaded. We're not going to use those plugins anyway, so we can just ignore those warnings. And we should have a ca.key here. Then what we can do is generate the public key, so a certificate for that private key. And it's going to be a self-signed certificate for the certification authority. The certificate is going to be valid for 10 years. The private key is ca.key. The domain name is going to be CUS. Evil silly scale. And common name is going to be, can be whatever. Let's call it strong swan root certification authority. And the out form is going to be a M, which is basically the hash form of the keys that we are outputting. It's just a standard. We output to the certification authority certificate. And we should have a ca.crt. Now what we can do is start populating all the files and directories that are going to be needed for the strong swan daemon to operate. So let's copy the ca.crt to etc swanctl, which is the utility that we're going to use to set up the IPSec server and client on the host X509 certification authority. And the reason why we copy with a move is because the certification authority certificate is going to be needed also on the other side on the client. We're just going to have it here. What we need to do on the server is to set up the PKI, generate a certificate request, have it signed from the certification authority, generate the certificate for server VPN so that we close the loop for the server, do the same thing for the client, and let them connect. So here, let's generate a private key for our server VPN. Now we should have a private key for the server. Let's generate a request for certificate for our server VPN. And here we have to pay attention to a couple of things. Since here we didn't use a fully qualified domain for the common name, in order for the client to authenticate the server, we need to use something that the client is sure of, which is the IP address of the server VPN. So now we generated a request for a certificate, and now we can issue that certificate for the server using the private key of the certification authority that lives here. So PKI --issue. Where is the certificate of the certification authority? The key for the certification authority, the type of certificate, serial number for the certificate, how long the certificate is valid, and now we should have the certificate, and we can remove all the requests because we're not going to use it. Not going to need anymore. And now we can move the files that we generated inside the folders that we're gonna need when we fire up the IPSec daemon. And we can remove both the key and the certificate because we're not going to need it anymore. Now, I can move over to the client. And let's generate a PKI here. We have a key. Let's generate a request. For And again, since here we didn't use a fully qualified domain name, we have to enter an IP address here. What IP address are we going to use? So let's think about how the connection from client 1 to server VPN happens. The connection happens through R1. And what does R1 do is, if we type IP tables -L -tnat, is basically doing a masquerading on the post routing, right? So what IP address is the server going to see? It's not going to see the private IP address of client 1 VPN. It's going to see the public IP address of R1, which is the IP address of the interface that connects to the server VPN, which is going to be 8.0.0.1. So here we have to put 8.0.0.1. So we have to be mindful whenever we are behind a network address translation, the IP address that the host is, or to use a fully qualified domain name here to make things easier, which can be like the email address of the employee. So now that we generated the request, we have to move the request over to our server VPN. And the way we do that is we're going to move, since we're not going to use it anymore, once we have the certificate, to shared. Now let's move from shared here, and let's then issue a certificate. VPN.crt, it's ready to go. Let's remove all requests because we're not going to need those. Let's move client1 VPN in shared. Let's copy ca.crt in shared. And now that we have everything here, what we can do is we can move client1 VPN.key into ATC is 1CTL private. We can move shared.ca.crt in ATC is 1CTL x509CA. And then we can move shared claim 1 VPN CRT into ATC. It's 1CTL x509. So now we have everything in terms of keys and cryptography setup that we need. We now need to configure the network side of things. So let's go here. ATC is 1CTL. It's 1CTL.conf. Let's delete everything and let's start typing. So connections. Road Warriors. And the pool of IP address for Road Warriors is going to be RW pool. Going to have local. We are going to be authenticated with the public key, which is in our server vpn.crt. And our ID is going to be our IP address. Remember the SAN that we put when generating the public key. Then we have remote. All the remote hosts are going to be authenticating with a public key. And then we're gonna push this route to all the clients that are going to connect. And then we have the pools configuration. And we're gonna have to match the name that we used here. So RW pool. RW pool. And the addresses that we want to have on that pool of Road Warriors is 192.168.100.0/24. So this means that we're going to have at most 254 hosts on the VPN. So this is done. Let's open up a teamwork session. We can type systemctl start strong swan starter.service. Perfect. Now we can load the configuration that we just typed. Let's type 1CTL-Q. So we successfully loaded one pool, loaded connection RW, successfully loaded one connection. Now we can go here on the client side, which is simpler. And it's 1CTL.conf. Let's delete everything. Let's type connections. Boom. The remote addresses. This is the server address that we want to connect to. We're not going to use any virtual IP. Our local configuration is going to be authentication with public key. certificate in client1 vpn.crt in the folders that we populated before. Our ID is going to be 8.0.0.1. The remote is going to be authenticating with public key. The ID is going to be 8.0.0.2. The children gonna have a home. And we're gonna have the remote push us a 192.168.0.0/24 start action start. So what this means is basically we're gonna populate our routing table with this children connection whenever the server pushes us. So we're just saying, hey, I'm expecting this kind of push route to be populated inside my routing table as soon as I establish the connection. So here we are. What we can do now is do the same thing. System ctl start strong1 starter.service, and we can do as one ctl -q, and we can see that we loaded the certificates and we successfully loaded one connection. Let's see if the connection opened up at all. And as you can see, we can ping the subnet, and we can ping the host. If we go on the host and open up a TCP dump session, you can see that ping is happening from the 192.168.100.1. What is happening here is that it's masquerading on output of the VPN. In this case, it's not an issue because phost has a default gateway to our server VPN, but in general, it's a best practice to have a masquerading on the output of the VPN on the server. But in this case, it's not going to matter because phost is going to have a default gateway on our server VPN anyway, so it's going to bounce it back here and it's going to forward it through the VPN. What we can see is that if we type IPR, nothing shows up. If we type IP root list table 220, we can see that 192.168.0.0/24 goes to 10.0.0.1, which is the router on device ATH0, and the source is the VPN. So it doesn't show up as clearly as OpenVPN, but everything is going on the VPN. And in fact, if we go here and then we stop the server, you can see that connection drops. We're now at the last section for this VPN and remote access part of the course, and we've seen with both OpenVPN and IPSec that to have people and devices join the network, we need to have a quite complex situation in terms of certification authority. Each host has to generate a request that needs to be signed by the certification authority that then issues a certificate, and what happens if we lose the key to the certification authority and whatnot. So what if we could use the same system that we had for SSH, where the client generates a private and public key, the public key gets installed inside the server, and now the client can authenticate with the server, and the same thing, the server authenticates with the client with its public key. can we build a VPN with that? And the answer is yes. And the name of the protocol that allows that is Wireguard. And it's a fairly new protocol, and the name of the game for Wireguard is simplicity, has to be fast, secure, and extremely easy configuration. We're going to see that the configuration is going to take like 4 or 5 lines of configuration file. Wireguard came out in the age of IoT, so it was meant to run on these very tiny devices that have very little hardware resources and couldn't rely on being tethered, meaning that they run on battery. And there's always on encryption, there's stateless design, cross-platform support, and we're going to see that this also the protocol itself is much leaner, meaning we do not use any negotiation of algorithms. Wireguard ships with one encryption algorithm, one integrity algorithm, HMAC algorithm, and one authentication algorithm, and that's it. The Wireguard architecture is extremely similar to whatever we've seen. The tunnel is always UDP. The local apps talk to the client here. The client has a Wireguard virtual interface that encrypts everything, sends it over the public internet, reaches the Wireguard server, and goes to the internal network. So we have seen that OpenVPN works at layer 4, so works at the TCP and UDP level, so that's where the encryption happens. We saw that IPSec works at layer 3, so at the IP level, so there's no notion of TCP or UDP, so that allows to save a little bit in terms of MTU. Wireguard operates at the layer 4 level as OpenVPN because it uses by default a UDP encrypted tunnel, which is the same thing that we did for OpenVPN. The architecture is extremely similar to what we've seen with OpenVPN without the bells and whistles. Wireguard cryptography, as I said, is fixed. It's not negotiated. These are the algorithms that are used. It uses Diffie-Hellman to derive the key. It's extremely similar to how SSH works without the negotiation framework. And the key management is the exact same thing that we've seen with SSH. The client generates a public key and shares it with the server. The server does the same. They both generate the same key with the elliptic curve Diffie-Hellman. There are no certification authorities, no PKI complexity, just public key cryptography, just like SSH. The entire connection establishment can be done in one round trip time, meaning that the Wireguard client initiates the connection and sends the public key, which is encrypted with the server's private key, and the server replies with a confirmation handshake, and at that point they're both mutually authenticated and the encryption can start. One round trip time, perfect for security, silent. There are many advantages. In fact, it's one of the most used nowadays protocols. One commercial product that has been spun off Wireguard is called Tailscale, which is the VPN that I've been using for the last couple years. And it's extremely fast, extremely reliable, and it's extremely lightweight. I'm running Wireguard on very small routers that are deployed overseas for IoT applications. So Wireguard has little to no overhead and can achieve near-line speed on modern hardware with minimal CPU usage, which is what you want for embedded devices. You can see a comparison with what we saw with OpenVPN and IPSec, but Wireguard trades flexibility for simplicity and security, which is often the right choice. We're going to see that one of that limitation is we cannot assign dynamic IPs to hosts that connect to the VPN. So we have a static binding between a public key and an IP that we assign. But that generally is not an issue because there are open source packages that can be used to provide that functionality. We're not going to see those, but it's extremely easy to integrate those add-ons on top of Wireguard. We're going to do the same thing that we've done for IPSec and OpenVPN. Take this lab, create a VPN between client 1 VPN and our server VPN. So remote access VPN, where client 1 is our remote worker, and this subnet is where we wanted to expose the remote worker, because there are a bunch of servers that we want to access, and in particular we want to access this P host. Now let's go into our lab folder and let's add into VPN WG, which stands for Wireguard. And also here we just have interface configuration, and inside client 1 VPN .startup and our server VPN we have the install of the packages needed for Wireguard. We can fire lab let's put the server here, let's put the client here. If everything went correctly, you should be able to type wg-h on the client and on server and see some output. If not, just clean the lab and restart again. I don't know why. I've seen like 1 time out of 10 it has some issues downloading the packets for some reason. Alright, so what we have to do is the same thing that we did for SSH, generating a private and public key pair for both client 1 and our server VPN. In the case of SSH, we didn't have to create a key for the server because the key generation process was part of the installation script of the SSH server. So it was it's shipped already with a public key, but in this case, Wireguard doesn't have different packages for client and servers, so we just have to do it on both sides. So let's start with the server, and we're gonna move into our root folder, and we're gonna type wg gen key, and we're gonna pipe it to private key, and from that we're gonna generate a public key inside pub key. So let's give it some numbers here. Let's call it r server VPN dot key. Let's call it r server VPN dot pub. And you can see we have both the public key and the private key here. Let's do the same thing here. WG. Let's move into our own folder. WG gen key client 1 VPN dot key WG pub key inside client 1 VPN dot pub. And also we have this thing. So now this is all the cryptography we need. We just need to start configuring the interfaces and the network side of things. So let's go on the server configuration, and what we're going to do is we're going to create a new file in IPSe Wireguard wg0.conf, and the name that you put here is going to be the name of the interface, like ATH0 is going to be wg0. So this is a interface which private key is this one. The address that we want to assign to this thing on the VPN is 192.168.0.1/24, and the port that we want to use is 51820. Then what we want to do is peer public key, and we're going to get the public key from here and paste it here. And then this guy, let's say you can take any address that you want in the /24 that we allocated for the VPN. On the slides, you're also going to see a couple firewall commands for when we set up and we shut down the actual VPN. And as I said in the IPSec lectures and OpenVPN lectures, in this particular lab, it's not going to matter. But if you're running the VPN and then the private network behind the VPN has multiple routers, you should be doing network address translation at the VPN gateway to make sure that those packets can be routed throughout the private network. So this concludes the configuration for the server. Now let's configure the client. And it's going to be extremely similar to Wireguard wg0.conf. Then interface, private key for the client, and here we have it. The address that we want to assign is, for example, 192.168.100.2/24. So this is where, in the theory part, I was saying there's no support for dynamic IP addresses, because here you have to specify an IP, otherwise that WG0 interface on client 1 VPN is going to be floating. Here, have public key, and here we want the public key of the server, perfect. Now we have the endpoint is going to be 8.0.0.2. At port we chose 51.8.0, and the allowed IPs, meaning the routes that we're going to push inside this VPN, are, of course, the VPN itself and the private network that is behind the VPN. And to avoid that the NAT kills our connection, let's have a keep alive here. Now what we can do is set up the server, and we can see that these are the commands that this WG quick did, and it set up a new interface which is WG0 with IP address 192.168.100.1, and we have new routes here for the VPN. We can do the same thing here, WG quick up, and we have the same thing here. We have a new interface WG0 with a new route. We have the routes to the VPN, and we have the routes to the subnet that is behind the VPN. If we look at the addresses, we have 192.168.100.2, which is the one that we assigned. And now if we try and ping the router on the VPN, it's going to work. If we try and ping the router on the private network, it's going to work. And if we try and ping phost, it's going to work as well. Now let's see what phost does see. So you can see that phost is looking at 192.168.100.2. What we can do is see what happens when we add the masquerade here. The target network is on Ethernet 1 on the server. And of course, when we bring the interface down, we want to delete with the -D that option. Let's bring the interface down and up again. You can see now we are executing the IP tables command. And now if we try and ping again, let's see what it changed. And you can see that now the VPN doesn't appear anymore, but we have the packets being masqueraded from 192.168.0.2 to 192.168.0.100. Again, in this case, we do not have a meaningful impact on the functionality of the network because phost has a default gateway on our server VPN anyway, so it really doesn't matter. But in real scenarios, when you're running multiple routers onto the private network, if you don't put a masquerade, the packets from client 1 to the server know how to reach the server. They get detunneled and then they get sent onto the private network, but nobody knows how to route them, so they get lost. And the only way to fix that is to add a masquerade on the interface that connects the VPN gateway to private network.